something is wrong with the universe. Not wrong in a way that scientists are quietly debating behind closed doors, wrong in a way that is forcing the most brilliant minds on this planet to rewrite textbooks, discard decades of accepted theory, and stare into their data with an expression that nobody expected to see on the faces of NASA astronomers: genuine fear. The James Webb Space Telescope was built to answer questions. Instead, it has done something far more unsettling. It has found things that should not exist, and the deeper it looks, the worse it gets. Nobody warned you that the universe was about to break. That is not an exaggeration. That is not a headline designed to get your attention and then disappoint you with mediocre information. That is the actual, documented, peer-reviewed, laboratory-confirmed situation that the world's leading astrophysicists are grappling with right now, in real time, as you read these words. The James Webb Space Telescope, the most sophisticated, most expensive, most powerful astronomical instrument ever constructed by human hands, has spent the last several years staring into the depths of the cosmos. And what it has sent back has not been wonder, it has been confusion, disruption. A creeping, spreading crisis that is quietly dismantling everything we thought we understood about how the universe came to be, how life might exist within it, and whether the foundational equations that govern modern cosmology are actually correct. Think about what that means, not just for scientists, for everyone. The James Webb Space Telescope completed its third full year of science operations in early 2026, and the discoveries continue to challenge fundamental assumptions about how the universe works. Galaxies that shouldn't exist at their observed distances, atmospheric compositions on exoplanets that rewrite habitability models, and stellar formation processes that contradict textbook explanations. Webb isn't just finding new things, it's forcing revisions to theories we thought were settled. That sentence, written by researchers tracking this mission, is one of the most quietly extraordinary admissions in the history of modern science. Because when the people who built the machine, who designed the mission, who spent 30 years and $10 billion bringing this telescope to life, when those people say the universe looks nothing like what they expected, you need to stop and understand what that actually means. But here's where it gets worse. The James Webb Space Telescope was not supposed to produce a crisis. It was supposed to confirm what we already believed. Scientists had a model, a beautiful, elegant, mathematically precise model called the Lambda CDM Standard Model of Cosmology that described how the universe evolved from the moment of the Big Bang, how matter clumped together under gravity, how the first stars ignited in the darkness, how galaxies slowly assembled themselves over hundreds of millions of years. It was not a guess. It was the product of a century of observation, calculation, and refinement. Physicists trusted it the way you trust the ground beneath your feet. And Webb was launched, in part to see that model confirmed in exquisite detail, to watch the birth of the first galaxies in the earliest epochs of cosmic time and say, yes, there it is, exactly as we predicted. Instead, Webb looked into the infant universe and found something that had no right to be there. Almost as soon as the telescope was switched on, astronomers saw something surprising. There seemed to be big, bright galaxies everywhere in the early universe. They had predictions about how many galaxies they should see and how large those galaxies would be, but there were far more of them than they had imagined. This led to a flurry of headlines and a whole lot of head-scratching in the field because, at first glance, the galaxies the astronomers were seeing seemed to be impossible. That word, impossible, was not used lightly. These are people who work with numbers for a living, people trained to resist hyperbole, people whose careers depend on precision. And they looked at Webb's data and used the word impossible. Read that again. Impossible. Now understand what makes them impossible. Under standard cosmological theory, the universe in its infancy, in the first few hundred million years after the Big Bang, should have been a place of chaos and simplicity. Hydrogen and helium mostly. Slowly cooling gas. Gravity beginning the long, patient process of pulling matter together into the first primitive stars. The universe was young, it was hot, it was unstructured, and the kind of massive, complex, brilliantly luminous galaxies that we see in the modern cosmos would have required billions of years to assemble. That is not an opinion. That is what the mathematics demands. You cannot build a skyscraper in a single afternoon. You cannot assemble a mature, structured, luminous galaxy in a few 100 million years. The physics will not allow it. Except Webb looked at the universe a few 100 million years after the Big Bang, and it found skyscrapers. In mid-2025, Webb identified a galaxy designated JADA's GS-Z14-0 at a redshift of 14.32, placing it approximately 290 million years after the Big Bang. At that point in cosmic history, there simply hasn't been enough time under standard models for gas to collapse, form stars, build heavy elements through stellar fusion, and assemble those elements into a structured galaxy with visible spiral features. 290 million years. In cosmic terms, that is a heartbeat. That is an instant so brief that by comparison, our own solar system, which formed about 4.6 billion years ago, feels like something that came out much, much later. And yet, Webb found a galaxy that looked, by all measurable characteristics, like something that should have taken billions of years to build. And this is where everything changes. Because JD's GSZ140 was not a lone anomaly. It was not one strange outlier that astronomers could dismiss as a measurement error or a calibration glitch. Webb has found far more bright, ancient galaxies than scientists expected, challenging previous theories about the universe's infancy. This unexpected population has electrified the community and raised fundamental questions about galaxy formation in the first 500 million years after the Big Bang, researchers wrote. An unexpected population, not one galaxy, not a handful, a whole population of objects that the most sophisticated cosmological models in human history said could not, should not, mathematically must not exist at the point in time where Webb found them. What most people are not seeing is that this is not a minor correction. This is not a case of scientists fine-tuning an equation or adjusting a variable. The bright end of the galaxy luminosity function at redshifts greater than 10 is significantly higher than pre-JWST models predicted, meaning there are more very bright, very massive early galaxies than theory allows for the time available after the Big Bang. Some researchers have proposed that these observations require revisions to the lambda CDM cosmological model, potentially invoking more efficient star formation in the early universe, modified prescriptions for stellar feedback, or even adjustments to fundamental parameters. Adjustments to fundamental parameters, that phrase, buried in academic language, is one of the most alarming things in modern physics. It means that the constants, the numbers, the bedrock assumptions that underpin not just cosmology, but our entire understanding of how matter and energy behave across time and space, those things may need to change. Think about what that means for everything built on top of them. But even this, even the impossibly early galaxies, even the crisis in cosmology, even the theoretical earthquake quietly shaking the foundations of physics, even all of that is not the discovery that has made scientists the most uncomfortable. That discovery involves a planet 124 light years away, a planet that Webb has now examined twice with 2 different instruments and 2 different wavelength ranges of light. And both times, it found something that, if confirmed, would be the single most important scientific discovery in the history of the human species. The planet is called K2-18b, and what Webb found in its atmosphere may change your understanding of your place in the universe. Astronomers using the NASA, ESA, CSA James Webb Space Telescope have detected the chemical fingerprints of dimethyl sulfide and or dimethyl disulfide in the atmosphere of the super-Earth exoplanet, K2-18b. On Earth, DMS and DMDS are only produced by life, primarily microbial life, such as marine phytoplankton. While an unknown chemical process may be the source of these molecules in K2-18b's atmosphere, the results are the strongest evidence yet that life may exist on an extrasolar planet. Sit with that sentence. The strongest evidence yet. Not a rumor, not a speculation, not a fringe theory proposed by someone outside the mainstream. A peer-reviewed finding published in the Astrophysical Journal Letters, emerging from the most credible space telescope humanity has ever launched. The strongest evidence yet that life may exist on another world. Here is what dimethyl sulfide actually is, and why its presence matters so profoundly. On Earth, this molecule, abbreviated as DMS, is produced almost entirely by marine organisms, specifically by microscopic phytoplankton living in the ocean. When these tiny creatures go about their biological processes, DMS is released as a byproduct. It drifts into the atmosphere, where it plays a role in cloud formation and contributes to the faint smell of the sea that you notice when you stand on a coastline. It is a molecule so intimately tied to biological activity on this planet that, for decades, astrobiologists have listed it as one of the most reliable potential biosignatures. A chemical signal that, if detected on another world, would strongly suggest that living organisms are responsible for producing it. And Webb found it, or something chemically indistinguishable from it, in the atmosphere of K2-18b, not in trace amounts, in quantities that stagger the mind. According to the research team, you would need thousands of times Earth's concentrations to be able to explain the data. Thousands of times. Not slightly elevated, not marginally above background levels. Thousands of times the concentration found in Earth's atmosphere. That number alone should stop you in your tracks. If a biosignature molecule is present at thousands of times the concentration you would find on a living planet, a planet already teeming with oceans of phytoplankton, then what does that imply about the biological activity potentially occurring on K2-18b? But here's where it gets more complicated and more important. The detection was not made once. A 2025 study used the Webb telescope's MIRI, the mid-infrared instrument, which observes in a different wavelength of light, offering researchers a new look at this intriguing world. This is an independent line of evidence using a different instrument than we did before and a different wavelength range of light. Yes, where there is no overlap with the previous observations, said lead researcher Niku Madhusudan of the University of Cambridge. That distinction is critical. When you use two entirely different instruments operating at entirely different wavelengths, with no overlapping data, and both instruments return the same result, the probability of a coincidental measurement error drops dramatically. This was not one fluke reading on one piece of equipment. This was a converging signal from two independent lines of evidence pointing toward the same extraordinary conclusion. The question is, what is K2-18b? The planet orbits its star in the habitable zone, and sometimes called the Goldilocks zone, which is the region around a star in which an orbiting planet might have conditions suitable for the emergence of life, such as the ability for liquid water to exist on its surface. It is not merely in the habitable zone by a narrow margin. It is squarely positioned in that zone, at a distance from its star that allows temperatures to exist within the range where water remains liquid. And water, as far as every line of scientific inquiry has ever determined, is the prerequisite for life as we understand it. No water, no life. Liquid water, and the door opens. K2-18b is what scientists call a Hycean world. That is a category of planet, relatively new to our classification system, that describes a world with a global ocean covered by a hydrogen-rich atmosphere. Imagine Earth, but instead of patches of ocean separated by continents, the entire surface is water. A planet-wide sea, kilometers deep, stretching from pole to pole with no land anywhere. Above it, a dense atmosphere of hydrogen gas, trapping heat, maintaining pressure, keeping that ocean liquid. According to theoretical models, Hycean worlds are potentially among the most habitable environments in the universe, perhaps even more so than Earth-like rocky planets, because the sheer volume of liquid water available would provide an enormous reservoir for life to develop, diversify, and thrive. It's important that we're deeply skeptical of our own results, because it's only by testing and testing again that we will be able to reach the point where we're confident in them, said Madhusudan. That's how science has to work. That caution is not cowardice. That caution is integrity. Because a false positive here, a premature claim of extraterrestrial life that later turns out to be wrong, would be one of the most damaging events in the history of scientific credibility. The pressure to be certain before saying anything certain is enormous. But the counter-pressure, the pressure of the data itself, is growing. Because even as the Cambridge team was publishing their detection, other researchers were examining the same data and reaching troubling complications. A group led by Luke Wellbanks showed that the apparent dimethyl sulfide signal could be swapped for ethylene, an unremarkable hydrocarbon with no loss of fit, and concluded that the data do not meet the standard of evidence for life. The same work found that the choice of how to bin the raw Webb data strongly affected whether the molecule appeared at all. This is where science operates at its most ruthless and its most honest. The data is real. The instruments are genuine. But the interpretation of spectroscopic data, the process of reading a planet's atmosphere by analyzing how it absorbs starlight at different wavelengths, is extraordinarily difficult. The signals are faint, the wavelengths overlap. The difference between dimethyl sulfide and certain ordinary hydrocarbons at these distances and these sensitivities can be nearly indistinguishable. This is not a reason to dismiss the discovery. It is a reason to demand more observation, more time on the telescope, more instruments, more independent analysis. And that is exactly what the scientific community is now doing. The real story is this. For the first time in human history, we have a specific planet in a specific star system at a specific distance with a specific set of measurements, all of which are consistent with the presence of biological life. The signal may not be confirmed. The alternative explanations have not been fully ruled out. But the direction the evidence is pointing, consistently, repeatedly across multiple instruments and multiple observations, is toward something extraordinary. And then there is the third front on which Webb is quietly rewriting everything. The one that involves not the scale of the universe or the possibility of life, but something even more fundamental. The existence of a class of objects that nobody knew existed until Webb found them. Objects so strange, so unprecedented, so resistant to existing theoretical frameworks, that scientists are still struggling to find a name that accurately describes what they are. For years, strange red dots in James Webb images left scientists puzzled. New research shows they are young black holes hidden inside dense clouds of gas, glowing as they devour their surroundings. Astronomers have uncovered mysterious little red dots that may not be galaxies at all, but a whole new type of object. Black hole stars. Black hole stars. Read that term carefully. A black hole star is not a black hole inside a star, the way you might imagine a parasite living within a host. What the evidence suggests is something far stranger. An object in which the black hole and the star are not separate entities at all, but a single unified structure, a gravitational paradox, a fusion of the two most extreme objects in stellar astrophysics into something that should not, by any conventional understanding of physics, be stable enough to exist. But here they are, hundreds of them, scattered across the early universe in Webb's field of view, glowing red in the infrared, unmissable once you know what you're looking at. What most people are not seeing is that the little red dots are not just scientifically interesting. They may be the answer to one of the deepest unsolved mysteries in modern astrophysics. Where do supermassive black holes come from? Every large galaxy in the modern universe, including our own Milky Way, has a supermassive black hole at its center. These objects contain millions or even billions of times the mass of the Sun. And for decades, astronomers have struggled to explain how they could have grown so large so quickly. Under standard models, black holes grow by accreting mass over time, swallowing gas, stars, and smaller black holes in a slow accumulation process. But the timeline doesn't add up. The supermassive black holes we observe in the early universe are too large, too soon. They grew too fast. The standard growth mechanism cannot account for their size, unless something else was growing them, something more efficient, something that could fuse stellar mass directly into a black hole from the very beginning, creating a shortcut that bypasses billions of years of slow accretion. Something like a black hole star. The James Webb Space Telescope's view of the infant universe has delivered genuine surprises. Bright galaxies, rapid star formation, and evidence of accreting black holes only a few 100 million years after the Big Bang. These findings have ignited debates about whether our best cosmological theories can survive new data. That phrase, whether our best cosmological theories can survive, is not rhetorical. It is a sincere, open question being debated at conferences and in journal submissions and in late-night conversations between physicists who have spent their entire careers trusting a model that is now, point by point, being challenged by the machine they built. In April 2026, in a conference room in Helsingør, Denmark, overlooking a strait between the Baltic and North Seas, more than 100 researchers from around the world gathered to discuss the puzzles of the universe's infancy. Colorful visualizations of dark matter, gas, and starlight danced on a projector screen. These are not fringe thinkers. These are not outsiders. These are the field's most respected minds, gathering not to celebrate consensus, but to confront a growing body of evidence that is pulling in directions nobody fully anticipated when Webb launched on Christmas Day of 2021. Think about what has happened in just 4 years. A telescope reaches its orbital position, it opens its golden mirror, it begins collecting light, ancient light, light that has been traveling for billions of years across the expanding universe. And in the patterns of that light, it finds galaxies that cannot exist. It finds a molecule associated exclusively with life on a planet in the habitable zone of another star. It finds entirely new categories of cosmic objects that require new theoretical frameworks to explain. And now, in 2026, it shows no signs of slowing down. As of early 2026, JWST continues to produce groundbreaking results at a pace that has stunned the astronomical community. Galaxies that shouldn't exist at their observed distances, atmospheric compositions on exoplanets that rewrite habitability models, and stellar formation processes that contradict textbook explanations. There is a pattern here, and the pattern is this. Nearly every major assumption that astrophysicists carried into the Webb era has been tested by Webb's data, and nearly every major assumption has been found to be incomplete. The early universe is not the quiet, simple, slowly awakening place that the models predicted. It is a place of furious, precocious activity. Galaxies already enormous, black holes already massive, heavy elements already scattered across space, as if the universe did not receive the memo about how long these things were supposed to take. Before JWST, astronomers expected complex galaxy mergers and widespread enrichment by oxygen and other products of stellar fusion to become common well over 1 billion years after the Big Bang. The discovery of a tightly packed collision of at least 5 galaxies just 800 million years after the Big Bang shows those processes were already underway far earlier than models predicted. 5 galaxies, already merging, already producing oxygen, already distributing the chemical building blocks of future planetary systems, at a time when, under the standard model, the universe should still have been in its infancy. This is not chaos. This is a pattern. And the pattern suggests that the universe is older in behavior than it is in age, as if some process in its very early moments accelerated the assembly of complexity far beyond what the physics of the Big Bang alone should have allowed. According to informed sources tracking the ongoing theoretical response to Webb's data, there are now 3 competing schools of thought among cosmologists. The first group argues that the standard model is fundamentally correct, but that our understanding of early star formation efficiency was simply too conservative, that stars formed faster and more voraciously in the early universe than models assumed, and that the equations need recalibration rather than replacement. The second group argues that dark matter played a more active role in early structure formation than previously accounted for, that dark matter's gravitational influence in the earliest moments created the scaffolding for galaxy formation far more quickly than the standard model allows. And the third group, smaller, quieter, but growing, argues that something more fundamental is wrong, that the cosmological constant, the expansion rate of the universe, perhaps even the timeline itself, may require revision. This third group is the one that makes everyone else uncomfortable. Because if they are right, the implications cascade outward in ways that are difficult to fully calculate. And yet, even in the middle of all this theoretical upheaval, Webb has continued to surprise in ways that have nothing to do with the large-scale crisis in cosmology. Using the unique infrared sensitivity of the James Webb Space Telescope, astronomers detected bright hydrogen emission from a galaxy at an unexpectedly early time in the universe's history. The finding is challenging researchers to explain how this light could have pierced the thick fog of neutral hydrogen that filled space at that time. That fog, called the Epoch of Ryanization, is the period in cosmic history when the universe transitioned from being opaque to being transparent, as the first energetic radiation from young stars began ionizing the surrounding hydrogen gas. Oh, it is one of the most important transitions in the history of the cosmos, and Webb is observing it in unprecedented detail, finding that even this transition happened differently, earlier, more violently, in ways not predicted, than the models assumed. A new investigation using the James Webb Space Telescope has uncovered an extraordinary concentration of small organic molecules deep inside the heavily concealed core of a nearby galaxy, including the first ever detection of complex organic molecules, frozen in ice around a young star in a neighboring galaxy, including building blocks that, on Earth, are associated with the chemistry of life, life's building blocks, frozen in ice around a young star in another galaxy. What this discovery represents is not just a chemical curiosity. It is a data point in one of the most profound ongoing investigations in science, the question of whether the molecular precursors of life are rare and precious accidents, or whether they are common, scattered throughout the universe, waiting for the right conditions to assemble into something that breathes, moves, and wonders about its origins. The emerging answer, from Webb's data, is leaning heavily toward the latter. But here's the tension that nobody is resolving neatly. Webb is simultaneously finding evidence that life's building blocks are widespread, and finding that many planets scientists hoped might be habitable are not. According to a new study using data from the James Webb Space Telescope, the exoplanet TRAPPIST-1d, which is similar in size to Earth, rocky, and resides in the habitable zone of its star, does not have an Earth-like atmosphere. TRAPPIST-1 was, for years, one of the most exciting solar systems in the known universe, a red dwarf star hosting 7 Earth-sized rocky planets, several of them in or near the habitable zone. The prospect that this system might host life generated enormous scientific enthusiasm. Webb has now systematically examined these worlds, and the results have been sobering. The atmospheres, where they exist at all, are not what we hoped. This is not chaos. This is science. The universe, Webb is revealing, is not going to hand over its secrets in the form that we imagined. It is going to force us to think differently, to question our assumptions about what habitable means, what life requires, what impossible actually indicates when it comes from a model, rather than from observed reality. Because the pattern of Webb's discoveries, taken as a whole, suggests that our models have consistently underestimated the complexity, the age, the richness, and the biological potential of the cosmos. What is actually happening, and this is the real story beneath all the individual headlines, is that we are living through one of the rarest events in the history of human knowledge. A transition moment, a paradigm shift in the literal sense, not just new information added to existing frameworks, but the frameworks themselves bending under the weight of what Webb is finding. Since the James Webb Space Telescope began scientific operations in July 2022, it has produced discovery after discovery that has forced astronomers to revise their models of how the universe formed, how galaxies evolve, and, most extraordinarily, whether life might exist elsewhere in the cosmos. 4 years into the mission, the pace of paradigm-shifting results has not slowed. If anything, 2025 and 2026 have produced some of JWST's most consequential findings. The most consequential findings in the history of the mission. 4 years in, and the pace is accelerating. That should tell you something about what is coming next. Because Webb is not finished. It has fuel estimated to last well into the 2040s. Its mirror is performing beyond specification. Its instruments are functioning at levels that exceed pre-launch predictions. And every year it remains operational, it accumulates more data, reaches more distant targets, examines more planetary atmospheres, and peers deeper into the epochs of cosmic time that have never before been accessible to human observation. JWST itself appears poised to drive a series of great expansions of the cosmic frontier. previously unimaginable redshifts, approaching the era of the very first stars, no longer seem far away, researchers have written. The era of the very first stars, the absolute beginning of structured matter in the universe. The moment, mere tens of millions of years after the Big Bang, when the first hydrogen atoms collapsed under gravity and ignited into the first nuclear fires. That era, which was, before Webb, completely beyond the reach of any instrument and may now be within sight. And if the pattern holds, if the universe in its earliest moments is even stranger and richer and more complex than what Webb has already shown us, then the discoveries of the next decade will make everything found so far look like a prologue. The question is not whether those discoveries are coming. They are coming. The question is whether the scientific community, the theoretical frameworks, and perhaps even the philosophical assumptions that humanity carries about its place in the cosmos, whether any of those things will survive them intact. Think about where we actually are. A telescope floating in the darkness, 1.5 million kilometers from Earth, pointing its cold golden eye at the oldest light in the universe, is telling us that galaxies formed faster than physics allows. That a planet 124 light years away may be breathing chemistry that only living things produce. That the universe contains entire categories of objects we had never imagined, and that the model we used to explain everything, the model that generations of brilliant people spent a century constructing, may be, in critical ways, wrong. What comes after wrong? What fills the space where certainty used to be? What theory do you build when the universe itself has declined to behave according to the one you already had? Those questions do not have answers yet. And that, perhaps, is the most important thing Webb has told us. Not any specific discovery, not any single measurement or detection or confirmed anomaly, but the broader message encoded in the sum total of everything it has found. The message that the universe is larger than our imagination of it, stranger than our mathematics of it, more alive, perhaps, in ways we are only beginning to suspect, than our loneliness suggested. Webb is not done looking. And we are not done being surprised. The next transmission from that golden mirror, floating alone in the cold between the Earth and the infinite, it may carry the answer. Or it may carry a question so much bigger than anything we have asked before that the answers we currently hold feel small and fragile by comparison. Something is coming. Webb can feel it in the light. The universe is not what we thought it was. And the telescope that showed us that truth has barely begun to show us what it actually is.